Okay, welcome to AP Calculus. This is our second half of our assignment from 5.3. And let's keep going. Estimate where f prime and f double prime are 0, positive, and negative. And this is our graph, as you can see, of plain old f. But the bad way to read this is to say f prime is 0. We should say where the slope is 0. First derivative, slope. So our slopes are 0 right here, and right here. And the key to this is they say estimate, because I'm looking at this and it looks like it's not directly underneath -1, maybe about -1.2. We got another level off. This one I'm pretty confident of. Their intention was that that's at 0. And this one this looks kind of like the same as the other. It might be an even function. So if I'm going to say 1.2, I might say plus or minus 1.2. Okay, so then where is f prime greater than 0? That's a bad way to read this as well. That is really, when is the slope positive? Well, the slope is positive when the function's graph is, of course, going up. And that happens from here to here. So if my -1.2 is accurate, that is -1.2 until I get to 0. And then again it is positive. The slope is positive from, if this is positive 1.2 out here, so in union with positive 1.2 to infinity. And then negative, when is f prime less than 0? That's when the slope is negative. Well, that is occurring when the graph is going down from left to right. So that is from negative infinity to that estimated -1.2 in union with 0 to that estimated 1.2. So again, just estimates. We don't know the exact values. And then when is f double prime equal to 0? Well, that's a bad way of saying that as well. That should say, when is concavity switching, or when is our cupping switching? So as I go through here, my cupping of the function is up until somewhere around in here I start cupping down. And that's a little bit arbitrary, tough to see, but it may be about right in here, and that looks like it might be at about -0.7. And then when else is that? We're really looking for inflection points when the second derivative is 0. Cupping down at some point in here, I start cupping up, and maybe that's kind of at the same spot. If this isn't even, maybe that's 0.7. Assuming this is an even function, we'll work with that. Okay, when is f double prime greater than 0? That would be when we are cupping up. So we're cupping up from negative infinity until we get over to -0.7, and then we're cupping down until we get over here in union with 0.7, and appears to be cupping up forever after. And when are we cupping down? When is the second derivative less than 0? Cupping up, starting cupping down at that estimated -0.7 until we get to, still cupping down until we get to that estimated 0.7. Okay? So we just have to read that right and realize talking about the second derivative may not be the best way to talk about this. We should talk about the cupping or the concavity. Okay, similar, but we got to do some backwards thinking on this problem. Estimate the intervals on f, on which f is increasing and decreasing, and estimate the x-coordinates of any extrema. But notice they are giving us, this is a graph of f prime. So this is a graph of the slopes of f. So if f prime is negative, then the slope of f is negative. Now I know the slope of f prime is positive here, but this is the slope. This is a representation of the slope of f, the values of f prime. So like right here, I'm down at -3. So the slope of f is -3. The slope of f is -2. The slope of f is -1. The slope of f is 0. The slope of f is 1, 2, 3, etc. So the slope of f is positive all through here and here. The slope of f is negative here. So I'm going to call it A, or just increasing. The slope, the f is increasing when the slope is positive, and the slope is positive here from -2, just on the other side of -2, until we get to, you could make an argument at 0, we'll talk about that one in a minute, but all the way to 2. So why is this not -2 to 0 in union with 0 to 2? I think I can explain this. The graph is going up because the slope is positive, and then the slope is 0. So it's going up, and then the slope is 0, and then the graph is has slope positive again. It's going up. This function is increasing at all times, and you may say, well, how is it increasing when the slope is 0? Well, if I was standing at 0, my next step would be uphill. From my previous step to get to 0, no matter where I started, would be uphill. So unless this came up and then leveled off for a while, then my next step would not be uphill. So I had a horizontal line as part of this, but this is just an instant where we're at 0. So we are increasing -2 all the way to 2. The function is decreasing on intervals where the slope is negative, and the slope is negative apparently from -infinity to -2 in union with 2 to infinity. Okay. Then estimate any local extremes. Well, the extremes happen, we know, when our first derivative or our slope is equal to 0. Now, they don't always happen there, but they can happen there. Here's a way we might want to think about this. We might want to think about this as a sign chart. So my sign chart, if I was doing this might be helpful to our increasing and decreasing as well. My sign chart, the slope has interesting things happening at, this is my y prime sign chart, at -2, at 0, and at 2. That's when we hit, the slope hits 0. The slope is beyond 2, the slope is negative. Between 0 and 2, the slope is positive, between -2 and 0, and negative here. So you can see we are increasing from -2 to 2, we are decreasing from -infinity to -2, and we are decreasing from 2 to infinity. And now we ask, where are our extremes? We'll take a look. I can draw a graph from this. Maybe I could do it from here, but we've certainly been doing that kind of thing from here. Since this kind of looks like a polynomial, or it doesn't kind of, it looks like a polynomial, it's smooth and continuous, I would expect the derivative of a polynomial is a polynomial, and the antiderivative of a polynomial is a polynomial. And that's kind of what we're talking about here, our antiderivative, getting back to y. Our graph should be going down, leveling off at -2. I'm going to redo this, so I'm right underneath that -2, leveling off there, going up and then leveling off at 0, but then going up again, leveling off at 2, and then going down after that. So when they ask, how about our local extrema? Well, take a look. We went down, we leveled off, we went up. So we have a minimum, a local minimum, at x equals -2. This is not an extreme, because it's going up and then going up, but we have a local maximum at x equals +2, because the graph is going up and then coming down. Okay, maybe this is a key player, because this is kind of something we've been using quite a bit and bridges the gap. But taking a look at first derivative and graphs of second derivatives requires a higher order thinking. We have to go backwards from what we've been really comfortable doing. Okay, the instructions for 26 and 28 are back to a particle. I like the fact that they tell me it's moving along the x-axis, because now when I describe the motion, I can talk about it moving left or right instead of in a negative direction or a positive direction. I still kind of wish they would say we're dealing in feet and seconds or miles and hours or something along that line, but we don't have unit measure. Okay, with a position function of x of t, so this is like my s of t, position. Find the velocity, first derivative, negative 2 minus 2t. Find the acceleration, derivative of velocity or second derivative of position is negative 2. I'm going to rewrite this because that almost looks like pi. Negative 2 minus 2t. Acceleration, negative 2. And describe the motion of the particle for t is greater than or equal to 0. Well, I'm going to start by saying at t equals 0, and I'm going to try to touch base each time with everything. Might even before I do that, here's a thought, since the acceleration is constant, the particle has a constant acceleration of negative 2, and that could be feet per second or miles per hour, but we're going to go with that for our constant acceleration, then I don't have to talk about it again. And then I could say at t equals 0, the particle, we're going to say particle, we're not going to say it. We don't want to be talking about it, and we're like, okay, is that the particle? Is that the graph of? We're going to be specific, no pronouns. The particle is at 6, or 6 to the right is at 6 on the axis. What's its velocity? We put in 0. It is moving. When I put 0 into velocity, I get negative 2 to the left at a rate of 2. Now you say it's negative 2. Well, I said it's moving to the left, so at a rate of 2. 2 feet per second, 2 miles per hour, whatever unit we're working with. Okay. The next thing we might want to do is talk about when it turns directions, or if it turns directions. It's going to turn directions when negative 2 minus 2t is equal to 0, or when t equals negative 1. And when does t equal negative 1? T does not equal negative 1, because we're dealing with just t is greater than or equal to 0. So this particle continues after that to move in it. Let's take a look. The bigger the value I put in, the more this becomes negative. Or the bigger the negative I get, I should say. I put in 100, I'm now continuing to move left. So thereafter, it continues to move left. Okay. So didn't really change positions on that. That would be something that we'd want to be talking about. Maybe we will on 28. Let's see. Accelerator velocity at time t is 6t minus 6t squared. Acceleration at time t is 6 minus 12t. I might as well get this out of the way. Velocity equals 0 when 6t times 1 minus t equals 0 at t equals 0 and 1. Kind of writing uphill here. And let's get started with this. So at t equals 0, the particle is at 0 velocity is 0, and acceleration is 6 feet per second, something along that line. So the next thing I want to do is talk about the next place the velocity might be 0, so I might be turning directions, and that happens at, oh, do I have where I'm moving to? Velocity is 0. So because my velocity is 0, I might need to talk about what's happening prior to getting to 1. So I take a look. As soon as I get bigger than 0 here in my velocity equation, I'm going to go right here. As soon as I get bigger than 0, like 0.1, I've got 6 times 0.1, 0.6 times a positive value, so we're going to begin to move to the right. Then, follow that. Let me do that one again. If I put in 0.1, I get 6 times 0.1, 0.6. I get 1 minus 0.1, positive 0.9, so I got positive times positive. Our velocity is about to become positive. That makes sense because if we're going at 0 and we're accelerating, then we're going to end up with positive velocity. Then the particle begins to move to the right. I can get away with saying right again because we're on the x-axis. Now I'm going to talk about at t equals 1, the particle comes to rest at, because velocity is 0, at when t is 1, I put 1 in here and I get 3 minus 2 at 1. And we could even say with acceleration, when we have 1 in here, negative 6. So if I was moving to the right and I came to a stop, my acceleration is negative. I'm changing, my speed is changing toward moving to the left. My velocity is beginning to try to push toward moving me to the left. Okay, now, since it doesn't stop again, I'm going to give the thereafter speech. Thereafter, the particle, since it comes to rest, let's go back review. So anywhere after 1, if t is 0, the particle is at 0, velocity is 0, and acceleration is 6, then the particle begins to move to the right. At t equals 1, the particle comes to rest at 1 with acceleration negative 6. So thereafter, I'm going to expect it to go to the left. Let's see what happens if I put something in beyond 1. If I put in 2 for 2 into the velocity. If I put in 2, I get 12 minus 24. Yep, it's negative. Thereafter, the particle, CLE. Did I do that earlier? Nope, CLE. Good. The particle moves to the left, and the bigger value I put in here for t, the more this is going to make this decrease with increasing moves to the left with increasing velocity. So since I'm saying moving to the left with increasing velocity, maybe I should say speed here, but I'm moving to the left with increasing negative velocity, and let's see, our acceleration is also going to be increasing. If that makes sense. And increasing negative velocity. Okay. May have a little challenge here talking about this increasing negative velocity. That may be a good discussion for class. Okay, continuing on. Approximate the times at which the particle's velocity and acceleration are 0. So here we're given, if you can see this right, a position curve. We've got a distance from origin, we've got a time in seconds. So we're going to talk about when the particle's velocity equals 0. Its velocity equals 0. Well, velocity is s prime of t. It's the first derivative. And if the first derivative is 0, the slope is 0. So we're looking for where the slope is 0, and the slope is 0 right back here. It looks like a tiny bit to the left of 2, and if I've got the same scale, that might be like, let's go, velocity of t equals 0 at maybe negative 0.2. Again, that's an approximation. We're approximating these guys. Approximately negative 0.2. Velocity looks like it's 0 up here. That is maybe just a little bit to the left of 4. Maybe 3.8. Velocity does not hit 0 here. It keeps coming down, 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 down. Now the velocity hits 0, and this one actually looks like it's about underneath 12. Now, I don't believe the back of the book talks about this, but boy, I think we could make an argument that maybe we've quit going up at this very end point. Maybe velocity is 0 right here at 16. Again, back of the book, the author of the book or whoever was creating the key for this maybe felt like that was still rising, but I think there could be an argument made. Okay, acceleration is 0. Acceleration of our position function is our cupping of it, and acceleration is 0 when the cupping changes from positive to negative or vice versa. So here we are cupping up. Somewhere along the line, I'm cupping up, cupping up. Boy, it looks like it's right in about here. I start cupping down right in there, and that is at about 1.5. I'm cupping down, cupping down, cupping down, and somewhere in here, about right in here, and you got to kind of eyeball this. It looks like it's cupping up. That looks like maybe about 5.6. Again, these are going to probably vary from the back of the book. Cupping up, cupping up, cupping up. Somewhere right around in here, we're cupping back down. So maybe at about 8.1, ballparking it. Now we're cupping down, somewhere still cupping down, somewhere about in here. We begin cupping up. That might be about 10.8. Cupping up, cupping up, cupping up. It looks like somewhere, boy, that one does look like it's right about in here at 13.4 maybe. Okay, so again, all of those are just approximations. A good question was asked in class today about this. What the AP test might do is they might have like a point A right here, they might have a point B right here, they might have a point C right here, they might have a point D here, they might have a point E here, they might have a point F here, they might have a point, actually might have a point G at this 0, H, I at this inflection point, J at this 0, K at this end point, L, something like that. And they may ask questions about at which points is the slope constant, or which point is the velocity 0, or which point is the acceleration increasing, or which point are we accelerating, decelerating. So you would list points where those occurred. So it wouldn't be this arbitrary, we're going to guess at some decimal value. Okay. 34 to 38, use the second derivative test to find the local extrema for the function, which is foreign to us prior to this section because we've been using the first derivative. Now, this is a little bit peculiarly named because we still need to discuss the first derivative. We're going to use the first derivative to find out any point or points where the function levels off. So we still want to find the first derivative. Of course, we have to do that to get the second derivative. In your book, by the way, this says x to the 5th minus plain old 80 plus 100, but that was a typo. There should have been an x in there. So I get 5x to the 4th minus 80. If I want to know when y prime equals 0, which I do, I get x to the 4th equals 80 divided by 5, 16, so x equals plus or minus 2. So we have a point at negative 2 something where it's leveling off. We have another point, might not be leveling off at the same height, at 2 where the function is leveled off. And now we want to use the second derivative. Y double prime equals 20x to the third, and that's it. Is that it? That is it. And we don't want to set this equal to 0 now. Setting this equal to 0 will be all about the inflection points, and we're looking for extremes. What I want to do, if I call this f of x and this f double prime of x, I want to find f double prime of negative 2 and f double prime of 2. F double prime of negative 2 is, in fact, I don't even really care what it is. It happens to be negative 8 times 20, negative 160, but what I really care about is that it's negative. And when I put in 2, I get 160, but what I really care about is that it's positive. If my second derivative is negative, my cupping is negative, and at negative 2, the graph looks like this. Therefore, we have a maximum. Didn't want to do that. I have a maximum at x equals negative 2. If my cupping is positive at 2, the graph looks like this, meaning I have a minimum, a local minimum, at x equals 2. And now, to find out where we're at, we just put 2 in here. Can we do that one? That is 32 minus 160. Ooh, it sounds like negative 128. We negative 28 here. Let's do that one more time. I get, oh, no, it's negative 32. Let's see, put in negative 2 plus 160 plus 100. That's 260 minus 32. So yeah, I was off on that one. Negative 32, because I got used to 32. Should just grab my calculator. 160, I'm stubborn. Negative 32 plus 260 is 228 for a maximum. And put in 2, and now I get 32 minus 160 plus 100, or negative 160 plus 132. Now I get negative 28 for my minimum. Okay. Same thing, and then I'm getting a little bit of a lag here, so before I move on after this page,